Today we are going to take a closer look to phase changes and diagram of state. The properties of each phase are determined by the balance between the potential and the kinetic energy of the particles. The potential energy, in the form of attractive forces between molecules, will tend to draw particles together. On the other hand, the kinetic energy associated with the movement of the molecules tends to disperse the particles. We can interpret the properties of a state of a matter, either gas or liquid or solid, in terms of dominance of either energy, kinetic energy or attractive forces. Transitioning from solid to liquid to gas requires energy to be added to the system and is therefore an endothermic process. This energy is required to overcome the intermolecular forces. On the other hand, transitioning from gas to liquid to solid is an exothermic process, with energy being given off when new intermolecular bonds are formed. Remember that breaking bonds is always an endothermic process and forming bonds is always an exothermic process. Now, if we look at these two flasks, both contain water, one is open and one is closed. Evaporation will happen in both of them, but in the open container, the gas that is forming, the water vapor, will be able to exit and disperse in the environment, and eventually all the water will evaporate, leaving the container empty. If the container is closed, as the amount of water in the gas phase will increase on top of the liquid phase, the chances that molecules will run into each other and reconnect through intermolecular forces will increase over time. And eventually, the rate at which molecules of water are condensing will become equal to the rate at which molecules of water are evaporating, and we will reach an equilibrium. The rate of evaporation is constant and depends on the temperature of the system. The rate of condensation initially is zero because there is no vapor on top of the liquid and will increase steadily, and eventually the two rates will be equal and we will be reaching an equilibrium. At that point, the amount of vapor will be constant and therefore the pressure inside the closed container will be constant over time. We call that vapor pressure for that liquid. Now, this type of equilibrium is a dynamic equilibrium. So we want to figure out what's the difference between a dynamic. Static equilibrium tends to occur, for example, in physics and engineering, when forces are balanced, in the sense that there is no resultant force causing a change in velocity or a change in direction. In chemistry, a static equilibrium occurs when the reaction goes to completion. So by the end of the reaction, the limited reagent is completely used up, and the maximum amount of products that we could possibly form is actually formed. So an example could be a reaction between sodium hydroxide and hydrochloric acid. Let's say we have an excess of sodium hydroxide. By the end of the reaction, we will have a certain amount of sodium chloride, a certain amount of water. All the hydrochloric acid will be used up because it was the limiting reagent, and the sodium hydroxide in excess will be left. But at that point, there is no reaction happening anymore, and therefore we define this equilibrium as static equilibrium. An example of a dynamic equilibrium is, for example, when we measure the depth of the liquid in a container that drains through a pipe at the bottom, and at the same time the liquid is replaced at the top using a pump. Or another example is the one depicted in this picture. We have a girl on the escalator. She's climbing and the escalator is moving in the opposite direction. If the two movements happen at the same rate, from the perspective of an outside observer, her position is going to stay constant over time. So there is an equilibrium, but it's a dynamic one because she keeps moving and the escalator is also moving. So the same happens with the evaporation. We reach an equilibrium, but some molecules of water are still evaporating and just other molecules to the same amount, to the same extent, are condensing. So we see in this slide two formulas that describe quantitatively kinetic energy. The first one tells us that the kinetic energy is proportional to the mass of the object that's moving and to the average velocity to the second power. The second formula tells us the relationship between kinetic energy and temperature. So T is the temperature in Kelvin. Kb is a constant, it's called the Boltzmann constant, and is equal to the gas constant divided the Avogadro number. So when we have a pool of molecules, of course we have an extremely, in 1 mole of gas we have an extremely high number of molecules. That velocity that appears in the formula is the average velocity. But of course if we have a large population of molecules, they are not going to have the same velocity. Some will be slightly slower, some will be slightly faster. So it's a bit like if I would measure the height of all my students, and let's say the average is 5 feet 8, but then some students are probably shorter and some students may be taller. And so I could put together an histogram with the distribution of the height of my students. So I could put on the y-axis the fraction of students with a certain height, and on the x-axis I would put the height. In this case here we have the speed on the x-axis and the fraction of molecules with that speed on the y-axis. And many distribution tends to be quite symmetrical. For example, your height, the height of my class would be pretty much symmetrical. You see that these curves are kind of similar to a Gaussian, but they are a little bit slightly asymmetrical, with a little bit more of observation on the high side on the right. So for the first curve, the one that's labeled T1, so it's the one at a lower temperature, the average is indicated by V1, right? So the average is this one, right? This is the average velocity. You see that it's a little bit ahead of the right, what would you think is halfway in the distribution, and that's because of this uneven shape of the distribution that's skewed towards higher values. The idea is that if we increase the temperature and we go to a higher temperature, T2, the average velocity is higher. So the distribution kind of moves towards the right, also gets a little bit more wider. So we kind of flatten the curve a little bit. So if we look for the value of velocity of kinetic energy, and therefore velocity that's necessary to evaporate, right? In this type of distribution curves, the area below the curve after that specific value of energy, so the area that's been highlighted here, give us the total number of molecules that have an energy or a velocity equal to that threshold or larger. So those is the fraction of the molecule that are able to evaporate. Now you can see that in the curve labeled as T2, the curve at higher temperature, that area is larger than the one you would have in blue for the curve obtained at a lower temperature. So increases the temperature, increases the fraction of molecules that have enough kinetic energy to overcome the intermolecular forces and are therefore able to evaporate. If we measure the vapor pressure of water at different temperature, we obtain a curve. And at 100 Celsius, the vapor pressure is equal to the atmospheric pressure. As you can see from the table, it would be equal to 760 torr. Now 1 torr is the same as saying 1 millimeters of mercury, and it takes 760 millimeters of mercury to make 1 atmosphere. At that point, water boils, as we all know. So the molecule of water will now transition to vapor, not just on the surface as it happens during normal evaporation, but everywhere in the body of the mass of water, where I can see forming bubbles, just because at this point the vapor pressure is equal to the atmospheric pressure. So the main difference between evaporation and boiling is that while evaporation happens at any temperature, boiling can only happen when the vapor pressure of the liquid is equal to the barometric pressure. Evaporation happens only at the surface, while during boiling, the transition from liquid to vapor happens everywhere in the solution. Most liquids share a very similar shape. So here you see the vaporization curves for diethyl ether, or that's also called simply ether, ethanol, that's common alcohol, and water. So diethyl ether boils at a much lower temperature than water, so it takes only 34.5 Celsius. So that's lower than your bodily temperature, that's about 37 Celsius. Because the vaporization curves is much more situated much more on the left of the graph. Ethanol boils at 78.5, that's kind of intermediate between the two, and water boils at 100. The fact that ethanol boils at a lower temperature than water is at the basis of the ability to increase the concentration of ethanol in a mixture of ethanol and water through distillation. Ether is a very volatile liquid at room temperature. It's colorless. It has a kind of a characteristic sort of sweet smell. It's used in the labs as a solvent, and it was one of the first anesthetics used for general anesthesia in the modern surgery. This graph is a diagram of state for water, so it's showing all transition from solid to liquid, from liquid to vapor, and from solid directly to vapor. We will talk more about it later, but for the time being, let's just focus on the evaporation curve, that is this one. And on this curve, we have highlighted this point, and that is the boiling point of water at when the pressure is 1 atmosphere. So that's the, let's say, standard pressure. So we call that boiling point 100 Celsius. We call it normal boiling point. But of course, if we would change the pressure, the boiling point would be different. So for example, if the pressure is raised to 2 atmospheres, the boiling temperature of the water would be raised to 120 Celsius, and that's the principle behind the pressure cooker. So when you're boiling something in water, as long as there is water, the temperature is going to stay constant at 100 Celsius because you have the change of phase. If, for example, you're cooking potatoes, you get boiled potatoes. If you would be frying potatoes, then the medium would be different. It would be vegetable oil that is a much higher temperature, around 300 Celsius. And so that's during the frying process, the temperature would stay constant at that higher value, and that's why you get a completely different texture and consistency of the food. So if you're increasing the temperature from 100 to 120, and that is obtained by a thicker pot that is sealed and has a valve that allows you to control the pressure, you raise the temperature to 120, that still gives you the same, let's say, taste and texture of boiling, but it has the advantage of shortening a lot the cooking time. So for example, you could manage to boil a potato in just 10-15 minutes. On the other hand, if you reduce the pressure by connecting the water to a vacuum pump, you would be able to boil water at room temperature. Now, the relationship between pressure and temperature, so the mathematical equation that describes that curve highlighted in yellow, is called the Clausius-Clapeyron Equation, and is presented here in a logarithmic form. The advantage of a logarithmic form is to avoid the curve and to rectify the relationship between pressure and temperature. Having a straight line is it makes much easier to produce a graph in a lab setting. Y is becoming a straight line. So you can see that if you plot on the y-axis the logarithm of p, And if you plot on the x-axis the reciprocal of the temperature in Kelvin, you get a straight line with a negative slope. The intercept is C. That would be the point at which the graph crosses the y-axis. That's not so interesting per se, but the slope would be the ratio between of course the slope is negative, so the slope would be equal to minus the ratio between the vaporization, the enthalpy, and the gas constant. So because the gas constant is known, this graph allows us to calculate the delta H vaporization of water. The Clausius-Clapeyron equation can also be rewritten in so-called two-point form. So basically what you can do is write this equation a first time for a value of P and a value of T. Let's call them P1 and T1. And then you rewrite it for a second value of pressure, so you would have P2 and T2. And then you subtract the second equation from the first one. And you get the equation that you can see here. So the advantage of this equation is that you can measure the, for example, the vapor pressure at two different temperatures and plug those numbers into the equation to calculate the delta H. Now, you need to be careful with the units. The delta H of vaporization is going to be an energy and is typically in joules. So the value of R is not going to be the 0.0821 that you've been using in the gas law, but it's going to be because that would be liter per atmosphere on top of the fraction. The R value that you need to use is 8.3145 joules per divided moles divided Kelvin. This equation can also be used for sublimation, so transition from solid to vapor, but cannot be used for fusion, for transformation from solid to liquid. So this is an example of a problem. We have the vapor pressure of ethanol at a first value of pressure that's given in torr. Torr is the same as millimeters of mercury, and the temperature is in Celsius. And then we are given the delta H of vaporization. That's in kilojoules per mole, and we need to calculate the temperature when the vapor pressure reaches 760 torr. That would be 1 atmosphere. So really consider that the equation would be given in the cover of the exam. So really the difficulties here is to keep track of the units, and then all you have to do is plug and chug. So you have your equation from the cover of the exam. You need to transform the temperature into Kelvin. You can skip, so if you want to stay safe, transform the two pressure into atmosphere. However, the transformation from torr, that's the same as millimeter of mercury, to atmosphere would consist into dividing both 115 and 760 by 760. And then you would calculate the ratio of that. So the two conversion factor would simplify. So the ratio between the pressure in torr is the same as the ratio between the pressure in atmosphere. So, if you are confident enough in your comprehension of math, you could skip that conversion. If you just want to stay safe, just go to atmosphere. So because the gas constant is in joules, you need to be careful and transform the delta H vaporization in joules. So you need to take 40.5 and multiply by 1000. So the unknown is T2, that algebra-wise, having the unknown there is going to be the worst case scenario, probably. So you get the temperature in 350 as 350 Kelvin. They are asking you to give the answer in Celsius, so then you need to go back to Celsius. That's 70-75. 77 Celsius. That makes sense because first of all, we kind of see in the other slide where more or less was the normal boiling point of ethanol, because being the pressure 760, that's the normal pressure. So what we're looking for is actually the normal boiling point. Also, the pressure is going up, so it makes sense that the temperature is going up. So we have a result that sounds reasonable. This graph shows you a generic phase diagram. A phase diagram is the combination of melting, vaporization, and sublimation processes. And in each phase diagram, you have areas and lines. So, for example, you can see the area that corresponds to the solid phase, the one that corresponds to the vapor phase, and the one that corresponds to the liquid phase. So any combination of pressure and temperature that's correspond to a point in the solid phase, for example, for that combination of pressure and temperature, the only phase that you will observe for that substance is going to be the solid phase, and that's going to be the most stable. Generally speaking, the solid phase is mostly stable for high level of pressure and low level of temperature, while the gaseous phase is more stable for high level of temperature and low level of pressure. And then you have this line. So for example, the blue line represents the vaporization curve. So for each combination of pressure and temperature that correspond to a point on this line, you have the coexistence of the liquid and the vapor phase. On the green line, you would have the coexistence of the solid and the liquid phase, and on the red line, you would have the coexistence of the solid and the vapor phase. There are 2 points that are particularly important. You have the triple point. And the triple point is the only combination of pressure and temperature for which you can have at the same time liquid, vapor, and solid present together. And then the other important point is the triple point, the critical point, sorry. The critical point is, as you can see, the vaporization curve has an end. So that means that for every temperature below the critical temperature, so for example, if I have, in this situation of pressure and temperature, if I keep the temperature constant and I start increasing the pressure, eventually I can manage to liquefy my vapor. But if I'm here, I'm above the critical temperature for the same value of pressure, and I start increasing the pressure, no matter how the pressure goes, I will never cross into the liquid phase area. So above the critical temperature, no matter how high the pressure, you cannot transform the vapor into liquid. So at this point, we can truly use the word gas. It's a more ideal behaving gas, as opposed to temperature below the critical temperature for which we have a vapor, in the sense that by increasing the pressure, it's possible to transform it into a liquid. Now, as we said, we can see that the conversion from solid to liquid, so the fusion curve, can have different profiles depending on the substance. For most substances, there is a positive slope. For water, we have a negative slope. So we will see more about that in the next slide. So for the time being, let's eliminate that part of the graph. So question, typically in tests, you get a diagram of state that is blank and doesn't have any reference point. So the first thing you want to do is identify which one is the solid phase, which one is the liquid phase, and which one is the gaseous phase. And a potential way to do that is to draw an horizontal line that crosses the phases, all 3 phases. And then you kind of intuitively can understand that by increasing the temperature, so by going through that line from left to right, you should encounter the solid first, then the liquid, and finally the gaseous phase. So that strategy should allow you to identify the phases. Once you have the phases, you want to look for the triple point. That's easy to remember because is the intersection of three lines, and the critical point, that's the end point of the vaporization curve. So let's compare the phase diagram for water and for CO2. CO2 has a typical behavior that you can see for the vast majority of the substances, but CO2 is often used as an example. There are a lot of points in that graph, but let's focus on B and H. So let's consider point B. For this combination of pressure and temperature, CO2 is going to be a liquid. Now let's imagine we keep the temperature constant and we increase the pressure. So we're moving upwards all the way to point H, sorry. So what happens is that by keeping the temperature constant and increasing the pressure, we are going to see that the CO2 is going to solidify. So it's going from liquid to solid. Why? Because solid has a higher density, so is more compact than liquid CO2. And that's what the vast majority of substances do. The liquids tend to be more expanded than the solid. So if you have a bucket with dry ice, the solid component will sink in the liquid CO2. If instead we have water, and water is pretty much the only substance that does this, in this case, let's consider the transition from A to G. So we start from A, at which water is solid, and then we increase the pressure and water would melt, and you would get to G, where water is a liquid. And this is because the unusual behavior of water is that ice has a lower density, so it's more expanded than water, and that's why ice floats on water, and that's why when you put something in the freezer, you want to make sure that the container, if it's made of glass, is not completely full. Otherwise, in the process of freezing, the ice would expand and would break the glass, right? So in this case, increasing the pressure favors the phase that is more compact. That would be liquid water. Now consider also that the slope of this line are a bit exaggerated, typically, just to be able to show the effect. The type of question that you can get in a test is to guess the nature of the liquid of the substance based on the slope of the melting freezing curve. So basically, if it's water, it should have this peculiar inclination towards the left. Any other substance would show an inclination towards the right. So basically, the solid liquid line for water, it's inclined towards the left because the solid is less dense than the liquid. As a consequence of this peculiar behavior of water, you have a phenomenon that's called regelation. So, and this, you can find actually a couple of videos on YouTube describing it. If you have a large block of ice and you need to do this outdoors because you need to have a relatively low external temperature, you can put a metallic wire on top of the block of ice and add two weights on both sides. Because of the weights, there's going to be a pressure applied on the block of ice, and this pressure will cause the ice to melt. As the ice melts, the wire will start going down through the ice, but because the temperature is so low, the liquid water above the wire will immediately go back to solid. So actually what happens is that the wires can go through, it's a relatively slow process, so the wire can go through the whole block of ice without actually cutting it. A more practical consequence of regelation is when you're skiing, the pressure, because of the weight of your body that's applied just underneath the skis, causes the snow to melt, thus creating a liquid layer that helps the gliding of the skis. So this is all, and see you at the next presentation.